Okay, now we're looking at problem number 2 in our book, and here we go again. I'm looking at a trig function. Well, I know there's no way of eliminating a trig function, and I should try the u sub, but I'm thinking if I let u equal pi theta, du will be d theta. That wouldn't get rid of that theta for me. So I know this is not a u sub. Instead, I'm going to let u equal whatever I can eliminate by taking enough derivatives. Well, in this case, that would be the polynomial, and dv will be whatever is left over. And if I take a derivative, that's d theta, and if I integrate, I'll get v to be the sine of pi theta divided by pi. So let's make a deal as well here. I should have put that here somewhere. Let me see, maybe I could squeeze it in. Let's do it right here. It's important to keep track of. And this is a note, something you should really get out of the way. If I take a derivative, if I was to take a derivative of e to the k times x, where k is a constant, that's e to the k times x times k. So if I integrate e to the kx dx, instead of using a u sub, since we're going to be integrating problems that take multiple steps, some 5, 7, or even 10 steps, this is going to be e to the kx. If you take a derivative, you multiply. To undo that, you would divide by k, and that saves you a u sub. Same deal here. If I was to take a derivative of cosine, that will be the sine negative times pi. Since you're integrating, to undo multiplication, you divide. And watch how this works. This turns out to be u times v right there. That turns out to be theta, the sine of pi theta over pi, minus the integral of v du. And that's going to be 1 over pi. I'm going to drag up front because that's a constant. Sine of, I'm so stuck on n, pi theta d theta. So this will be theta divided by pi, the sine of pi theta, minus 1 over pi times, what do you take a derivative to get? Sine negative the cosine of pi theta, and you divide by pi again. So my final answer is theta over pi, the sine of pi theta, plus 1 over pi squared, the cosine of pi theta, plus. And that would be it. Let's get the next problem on. I'm glancing at number 4 and I'm thinking, well, let's see. If I let u equal the angle, du will be dx. That wouldn't get me anywhere. So that's like you saying the integral of u squared, the sine of u du. Well, all what you did was a letter change. So you shouldn't really try the u sub, and you should try the u sub on every problem, but you shouldn't think that it's going to work on every problem. And you should attempt to do it the way we're going to be doing it from now on. That is, every time you want to do it, you glance at it and do it mentally. There's nothing wrong with you writing that down. Well, I know what I'm going to let u equal. I'm going to let u equal x squared. And dv will be the rest, sine of x dx. Very good. du is 2x dx. And if I integrate, I'll get v to be negative the cosine of x. So this is going to equal u times v, negative x squared the cosine of x, minus the integral, going to squeeze this to the right a bit, minus the integral of u dv. The negative times the negative will make that a positive. I'll take the 2 up front, x cosine of x dx. Well, that didn't solve it fully. I should have known that already, because to eliminate an x squared, don't you need to take a derivative twice? Which means I'm going to have to do integration by parts twice. So I should be patient when I do this. That is, I'm already aware I'm going to do integration by parts again, but keep in mind, I'm going to only apply the second integral I'm going to only apply integration by parts on that integral. I'm going to let u equal x. du is dx. dv will be the leftover. And if I integrate, I'll get v to be the sine of x. So this integral is going to give u times v minus the integral of v du. And that would be a negative x squared, the cosine of x, plus twice x, the sine of x. And do you agree that the integral of that is negative a sine? Is a negative cosine times a negative. That will be a positive cosine of x multiplied by 2 plus c. Now luckily somebody made an observation and saved us some time. So the way it works, there are 3 types of integration by parts. There are really 2, but I'm going to say 3. One type of integration by parts that you integrate once. Another part that you integrate multiple times. So something like the next example, let me show you and show you what somebody came up with. So if I look at the following problem, I am aware how this works and have a good idea. That is, I'm going to have to use integration by parts 4 times. It's not that bad, it's just long, right? So if I start with u equal p to the 4th, du is 4p cubed dp. And if I let dv equal e to the negative p dp, and I integrate, v will be e to the negative p. When you divide by a negative 1, that's the same as multiplying by a negative 1. And this is going to equal u times v minus the integral of v du. That would be a positive 4 p cubed e to the negative p dp. So somebody made this observation, and let's go back. Somebody made the observation that you're always multiplying this way, and said, you know what, let me try. What if instead of doing this 4 times, you know, I'm going to have to do this now. I'm going to let u equal p cubed and dv equal e to the negative p dp and proceed. They said, instead of that, why don't I let u equal from the beginning, start with p to the 4th. You take a derivative, 4p cubed. If I was to take another derivative, that's 12p squared. Another derivative, 24p. Another at 24. So I keep on taking derivatives until one of those disappears. And if I let dv equal e to the negative p, then if I integrate, divided by negative 1. If I integrate, divided by negative 1. If I integrate, divided by negative 1. If I integrate, and said, look, you happen to multiply across. So if you multiply those should be the results. To compensate for this minus, you know, when you subtract, he said, let the first one be positive, because normally you just multiply those, but you subtract the next one. So just alternate on the signs, and that'll do the trick. And he was able to look at this and say, well, that is going to be the product of those, the product of those, the product of those, the product of those, and the product of those. So if I go by those and just fill in the blanks, that's negative p to the 4th e to the negative p, negative 4p cubed e to the negative p. Negative times a positive is a negative. The green, 12p squared e to the negative p. The pink minus 24 p e to the negative p, and a minus positive times a negative at 24 e to the negative p plus c. Instead of doing integration by parts 4 times, that's what we'll get. So if I was to say, you know what, let me see if that works on this. If I was to say, you know, I have the answer, that's why I'm doing this one. So if I was to look at this problem, number 4 that we already did, if I was to follow his trend and say, you know what, since I have to do integration by parts, if I'm going to do integration by parts once, I really don't need a shortcut. If I let u equal x squared, a derivative will be 2x, a 2, and a 0. If I let dv equal the sine of x, an integral will that would be, so what do you take a derivative of to get a sine, negative cosine of x, negative sine of x, and a cosine of x? And if I do the same idea, I'll start with a plus and alternate on the signs, I should get and one can use this shortcut anytime you want. I should get negative x squared the cosine of x. Negative times a negative is a positive. 2x the sine of x. And positive times a positive is a positive. Twice the cosine of x plus c. And I could match those answers, this answer and this answer, and you notice we get the same exact answer. So this shortcut works really well. If you have to do integration by parts more than once, then you should use it. Otherwise, no need to use it. The next problem up is number 18. So I notice this is a polynomial. This is not. Well, I can't eliminate e to the r. That will always be there. So if I do this, saying, you know what, let's do it the long way. Let u equal r squared plus r plus 1. du will be 2r plus 1 dr. dv would be e to the r dr, and if I integrate, I'll get v to be e to the r. I'm just doing this to convince you. So it's going to be u times v, r squared plus r plus 1 e to the r minus the integral of v du. And if I let on the next stage u equal 2r plus 1, du is 2dr, dv would be the rest, which is e to the r dr, and if I integrate, I'll get v to be e to the r. So this is going to be r squared plus r plus 1 e to the r minus, now the green is going to be that second integral. What comes out of the green is u times v minus the integral of v du. I'll take the 2 up front, and that is e to the r dr. So my final answer would be r squared plus r plus 1 e to the r minus 2r plus 1 e to the r plus twice e to the r plus c. And let's make sure we see solid how this works. Somebody might have looked at this and said, wait a minute, I'm going to go for the shortcut. I'm going to let this be r squared plus r plus 1. A derivative would be 2r plus 1. A derivative will be a 2 and a derivative will be a 0. dv is simply e to the r, integrate, 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 and if I multiply across, start with a positive, alternate on the signs, there it is. That would be the product of those. That is r squared plus r plus 1 e to the r minus 2r plus 1 e to the r, the product of those, plus, and what do you know? Those are the same. Next problem up. Well, we know for sure. I try not to use the word easy, but I see an integral with a log in it, or an inverse trig function. It's an easy problem. Why is that? There is one way of doing the problem, and that's it. And how is that? You must let u equal the natural log, or the log, or if you see an inverse trig function, you must let u equal that. And if I take a derivative, wouldn't that be 1 over x dx? So I try a u sub on every problem. There it is. And do you notice that this is actually this? So this will be the integral. My substitution will be the u, but it's being squared. And du will simply be the rest. Isn't that like saying u to the negative 2? Add 1 to the power, divide by that. Wouldn't that be negative 1 over u plus c? And what was u? And that would be my final answer. So I didn't need integration by parts on this problem. And that's something you should try on every problem. Now, let me do another problem really quick. Here's a problem. Normally, I look at this, say, wait a minute. If I let u equal the angle, right? du will be 3x squared dx. So I'm glancing at this, saying, you know what? I don't need integration by parts. If I let this be u, that's really the sine of u. And if I look at x squared dx, that is simply du with a price of 1/3. That's easy. That is 1/3 times negative the cosine of u plus c. That is negative 1/3 the cosine, and u was what? And there it is. So you shouldn't really jump the gun every time you look at a problem and say, oh, let me try integration by parts. The reason parts wouldn't work, and we know it doesn't work, because if I let dv equal the sine of x cubed, I don't know how to integrate that. That's not as simple as we think. Alright? I'm going to shrink this a bit and fit the last problem there. Actually, I'm going to shift the whole thing to the left a bit. Okay, and now if I work on the last problem, actually I can get a lot of space if I just move this underneath. There we go, much better. Yeah. Okay, let's get this out of the way. If I glance at this, I just mentioned, you see a problem with an inverse trig function. That's a very easy problem. You let u equal that for starters. And what's the derivative of that? That's 1 over the square root of 1 minus x squared dx. Well, look at that. What do you know? There's my u, and there's my du. So this is the integral of u happen to be the sine, but it's being squared du. And I know how that works. Add 1 to the power, divide by that. And if I go back for u, I know what u is. U was the sine inverse of x. Okay, I'm going to make that a bit bigger. That's going to be the sine inverse of x cubed divided by 3 plus c. There's our first assignment. Now, I do know I started with 8.2. I do 8.1 after. I do things out of sync a bit. This homework is on page 471. You're going to do number 1 through 19 When it says odd / every other odd, it's your choice. You could do every other odd. If you feel really comfortable with these problems, then you're fine. If you feel you're hazy, then you should go back and do all the odds. And 31 through 37, every other odd. In case you don't know what every other odd means, 31, 33, 35, and 37, those are the odds. You do when you skip one, but you always do the last problem. Alright? And if you're not sure, just ask me and I'll show you. And we will finish this section in our next class meeting.